Welcome, and my name is Mayur. I'm the Chief Data Scientist at Flipkart and also the VP of Engineering. In my role as the Chief Data Scientist, I mentor and oversee all the data science projects that we run at Flipkart. And also in my role as a VP of Engineering, I lead the search and recommendations charter. Today I'll be only focusing on the search part of it. The goal of the talk is to sort of give you what it means to do e-commerce search, to sort of familiarize you with some of the challenges in e-commerce search, and then with a very high level give a description about the tech platform that powers the search at Flipkart. Now clearly whatever I'm presenting here is in the context of what we have done at Flipkart, and but I think you might see very similar patterns in other e-commerce companies as well. So I guess a lot of you here already know Flipkart. It is the leading e-commerce company in India. We do about 8 million units. That's how much units are sold on our platform every month. Every day we get about 10 million visits. We have 21 state-of-the-art warehouses, or what we call as the fulfillment centers. And in terms of our users, there are two types of users, our customers and our sellers. We have about 100,000 sellers and 100 million registered users. So, fairly big footprint all across India. Anyone who has used Flipkart, there's a good chance that they have used search on Flipkart. Whether you use the desktop, whether you use the mobile app, search is a very prevalent and very important feature. Like, there's a search box, you type in your query there, you type in what you're looking for, and what you'll get back is a ranked list of products for what you're looking, right? So this is how most people find products on Flipkart. But what people also don't know is that other finding methods like recommendations, merchandising, which is basically promotions that we run on our homepage and so on, are effectively using Flipkart in the form of a pre-populated query. So when you click on one of those recommendation cards, or when you click on one of those tiles on merchandising, at the end of the behind the scenes what's happening is you're being taken to a search results page. So if you take both of these into account, then search accounts for a huge fraction of our business, like about 70-80% of units GMV. GMV, by the way, for those of you who are not from the e-commerce domain, stands for the gross merchandising value. That's just the dollar amount of the business that we do on our platform. So about 70-80% of our business is powered by search. So clearly one of the most important discovery mechanisms is search. Let's look at the different features that our search uses, and how that has a very important implication for the kind of system that we need to build. Before I go any further, let me introduce a couple of terminologies that are very common in e-commerce. One is a product and the other one is listing. A product, as the name suggests, is just the information about a specific product. Like, for example, it could be this mic. You might have a title for it, you might have a description for it, an image, maybe what the brand is. So anything that is specific to the product is what that particular entity is. And then there are listings. A listing is nothing but a pair of a seller who is selling a particular product. And remember, for every product there might be more than one seller who is selling that particular product. And every seller might come in with a different price that he is offering. There might be offers associated with the his listing. So all of that is another entity and an important one in the space of e-commerce. So as a search, what we are basically doing is we are searching on a combination of a product and all the listings associated with that particular product, right? Because that's what is important from the perspective of answering your queries. Now, as you might have noticed, I would like to draw some parallels with web search. And what you will notice that what constitutes a document in our case is not a pure text document. Of course, there are elements of text. There is a description associated with the product, there is a title associated with the product, and so on and so forth. But there is also a lot of structured information associated with this particular document, namely things like its price. What are the offers associated with it? So what is its MRP? How much is the discount on it, right? What is the time it takes to deliver this product to you, and so on and so forth. So it's kind of a hybrid between a structured and an unstructured search, and that's what makes e-commerce search particularly challenging. Moreover, these signals in terms of how fast we can get the product to you, what is the price associated with the product, etc., are used very heavily in our ranking algorithms. Not just the fact that we use them sort of behind the scenes in figuring out what are the best products to show to you, it is also, these features are also exposed to the users directly in the form of search features. So as you might see on the screen there, you can sort based on price, can filter based on price, you can filter based on some other attributes and so on. Now the moment you expose these signals to the users, like the onus on your system to give very high fidelity results suddenly goes up. Like for example, I cannot say that I cannot afford to be half an hour delayed in changes in prices. I could do that if I'm just using it behind the scenes and the user doesn't directly know about it, because the search function is complex. But when I'm exposing that to the user, I need to make sure that our system is very up to date with the kind of updates that are happening with respect to any attributes related to this product. Now what complicates the matter is the fact that the rate of update associated with these features is extremely high, as I'll talk about shortly. So to summarize kind of the main challenges, right? First of all, e-commerce search is not web search. You're not doing a pure text search on documents, right? Documents have a structure to them. As I said, they have a hybrid between a text document and a fully structured document like what you would typically see in a database system. And it's this hybrid structure that imposes sort of the challenges. And because the documents have a structure, the fact is that the queries, even though they might appear like just keyword queries and textual queries, they also have an implicit structure. For example, very often the query that we might see is black shoes under 1,000 rupees. Now, if you think of it, you could very well express this query as a SQL query. Now, of course, we don't expect users to type in SQL in our search box, right? So we have to interpret the fact that here is a person who's looking for products in the store shoes with color equal to black and price less than or equal to 1,000. So there's a very inherent structure to the query, unlike just token matching that is kind of more prevalent in the case of web search. And that's a challenge to understand the intent behind each query. So in terms of challenges, right, for a company like Flipkart, at the scale that we are operating, we have a huge collection of these documents, a fairly heavy long tail as well, and an extremely high rate of updates associated with these documents. Like the rate of update on a normal day is in the few thousands per second, and it can go an order of magnitude higher on our sales day and things of that sort. So to be able to keep up, so what we need to build are these extremely fast-paced distributed systems that can keep up with this rate of update. Furthermore, when it comes to the kind of ranking that we are doing, again there are a bunch of factors that we need to take into account. For a query like saris, the results that you might see in Pune are very different from the results that you might see in Bangalore, which are very different from the kind of results that you are seeing in Kolkata. And there are many reasons for it. The fact that the kind of saris that are commonly sold in each of these geographies are very different. Even though there might be certain saris that are universal, even then the availability of a sari might be there in one area but not the other. So our search and our ranking is very geo-specific. And it's not one simple metric that we are trying to optimize when we come up with a ranking function, but it's a very multi-objective function where on one hand we are trying to improve our business, wherein we are trying to sell more units, we are trying to do more GMV, but then on the other hand we also need to be aware and be very cognizant about, are the users finding the most relevant products, are they sort of going to be engaged with our site, and so on and so forth. And then there is advertisement revenue as well that we need to make on our site, so that also has to be factored in. Now, of course, there are a bunch of challenges, but there are some opportunities as well. One of the things that we have noticed is that we get a fairly high fraction of broad queries. Users just come to our website or app very early on in the funnel, meaning they just know that they want to buy a shoe. They don't know anything more than that. So you'll see people typing in shoes, saris, mobiles, cases and covers, and things of that sort. And therein lies the opportunity for us to personalize our search results for them, to do a certain amount of demand shaping and so on. So there are some good parts as well. So with that background, let me give you some numbers to tell you the kind of system that we have running, right? As I said, we get about a few 100 million queries in a week, roughly of the order of hundreds of millions. The kind of latencies that we see, these are internal latencies, and what you might see on your client might be very different because the network adds latency on top of it. But internally, we see the fact that our system is able to respond to queries in 100 milliseconds on an average. The median is 50 milliseconds, and the 90th percentile is around 500 milliseconds. Now, the where this latency comes from is based on the number of documents that match your query. For a broad query like sari versus a very specific query like Samsung Galaxy E6 black, the number of documents that match are very different. And to give you an idea, the 95th percentile, we are scoring about 200 to 500,000 documents. And as I said, for that we are giving back results roughly in the order of 500 milliseconds to 1 second kind of a thing. And the 99th percentile can go really high, like 500,000 to 3 million plus. Now, in terms of how well we are doing, one of the metrics that we really care about is the click-through rate, or CTR. And on an average, our CTRs are around 50%, which means 1 in every 2 queries is successful. A successful query is defined as one on which a user ends up clicking on a product page. Now, there might be more than one product clicks on the search results, but we just count it once because we are measuring this at the search query level. So what I want to do for the rest of the talk, it's kind of broken into 2 parts, and this is kind of the more technical part of it. In the first part, I will cover the system aspects of it, and clearly I cannot go into the details. What I would like to cover is just the functional and architectural overview of the search platform. And in the second part, I will cover the kind of the more quality aspects of it, like how do we make our relevance of our products better? How do we understand the query better? What are the challenges in that? And that is kind of the more data sciencey aspects of my talk. So before we go on any further, just wanted to let you guys know that Flipkart operates its own private cloud, and it's a fairly powerful one. So I mean, this is a typical rack that we have in our data centers. We have 2 of them, one in Chennai and one in Mumbai, and we have about 1 million cores available throughout our private cloud, 2.56 petabytes of RAM, about 120 petabytes of disk, 1 petabyte of SSD, and so on. So a fairly powerful cloud infrastructure, I would say. So coming back to search, there are 2 very high level components in search. One is the serving part and the other is the ingestion part. So the serving part is the one that is actually interfacing with the external clients. Whenever a request comes in or a search query request comes in, it is the one that is computing the answer and sending you back the results. It basically has at the heart an index of all the products and listings which are up to date. So as I was saying, the serving part is the one kind of is that answers the queries, and at the heart of it there's an index which is up to date and contains all of your products and listings. Now the other part is the ingestion part, whose main job is to keep this index up to date. It talks to the other data source systems, like for example in an e-commerce, there is a team that is responsible for maintaining the catalog, and it has microservices that tell you up-to-date information about when products change, new products come in, and so on, right? There is a system that tells you about, there's an inventory manager who tells you, how many units are remaining of every product or every listing. There is a pricing engine which keeps changing and updates the prices, and so on and so forth. Now this ingestion system keeps listening to these external sources of data, and whenever anything changes, it makes those updates into our index, right? So that's at a very high level the split between these 2. Now here is kind of a very functional view of what needs to happen in an e-commerce search, right? Let's begin from the top. At the top you have a typical proxy. So all requests to our search platform, all ingress and egress requests go through this proxy, and it handles 2 functions. One is the performance aspects of it, things like caching, rate limiting, query validation, and so on. And the second aspect is, given a query, it builds the context around it, like what is the location from where this query is coming, who is the user who's doing the query. Let's try and figure out what is the profile of this user. So it builds all of this context to pass to the other functional blocks. The second part is kind of the magic where the data science happens, or where the query understanding happens, right? As you'll see later on, the queries that we get have a huge variance in terms of their quality, the spelling mistakes, and so on. So it is our job to understand what the intent of the user was. So there we do things like spell correcting the query, synonymizing the query, understanding what this query is about, figuring out the structural aspects of the query, and so on and so forth. And what the output of this particular functional block is basically a query that you can send down to your index. Think of your index as basically Solr or Lucene for people who are familiar with web search, right? So you need to have a matching query, and you need to have a scoring query, a retrieval and a scoring query. So taking the user query and the context associated with it and converting that into the query that you can send down to your Solar Lucene is the job that this particular function does. From there we go to a search broker. Now why do we need a broker, right? At our scale, we cannot have our index sitting on one box. We certainly need to make it distributed. We need to shard our search indexes. So what this function does is when a query comes in, it basically farms out that query to all the shards, gets back the results from all of them, and then merges them or blends them. This is fairly standard when it comes to distributed search. And the last part, of course, this is the main workhorse, the actual index or the searcher. Like given a query, and when I say query here, this is not the user query, but kind of the reformulated, annotated query. It actually goes over the index, finds all of the documents that are matching for this particular query, and scores them. So scoring happens in two phases. There is a first phase where we do certain amount of scoring, and it has to be really quick. Remember the numbers I showed you earlier? Like, at a 95th percentile, you're looking at like 500,000 documents matching, right? I agree that it is being done in a distributed manner, but even a single box needs to handle a lot of these documents. And so quickly scoring of these documents happens in the first phase. Then once you get back all of your results from different shards, and you take your top 200 or 400 or some number, you do another round of rescoring or re-ranking. That's where you do your more computationally heavy things, like looking up a machine learning model, or looking up the latest values for availability, serviceability, and so on, right? So those might require some remote procedural calls and things of that sort, and therefore you want to do that only on a smaller subset of your documents. So that is kind of the functional view of what needs to happen. Now, of course, there are like 9 ways to skin a cat, as they say, and it's not that every e-commerce search is doing it this way, but it's fairly typical. Now, how does this translate into the underlying architecture? Like, this is what a typical architecture looks like in e-commerce, and again, this is in the context of Flipkart. Now, the way architecture is different from a functional view is that a single system might be sort of multiplexing or doing two functions at a time. So let's see how it works in our case, right? The green boxes are the ones that are external systems, internal to Flipkart, of course, and the blue boxes are the ones that the search platform is responsible for. So on the top, you have your clients. They are catering to your mobile apps, mobile website, desktop, and so on. And those are the ones that are sending the queries to us. On your top and left are, as I said, the other internal systems, the one that is giving you information about your catalog, about your pricing, about your availability or your inventory manager, and so on, right? And what you have, the top blue box there is your proxy, right? The proxy is actually doing two things here. So if you look at the previous functional view, one, it is of course doing the job of the proxy where it is doing your caching and query validation and so on and so forth. But on the way back, it is also sort of doing your level 2 scoring for yourself. So two functional aspects are merged onto this. Now, if a query is not present in the cache, then of course it will send down to the middle box, the broker. You can ignore the other boxes for now on that same level. Very briefly, what they are, there are other functions that search supports, like auto suggest, right? In the context, when you start typing query, if you've seen in Flipkart or most other websites, it will try to auto complete that query. So that service is also behind the same proxy, and that's what I've shown there. But let's focus on the main search aspect of it. So you have your broker. Now again, in this case, what we have done is this broker is handling two functional components. One is your query understanding, analyzing of the query, figuring out synonyms, spell corrections, and so on and so forth. And we'll look into the details of that a little later. And it is doing the scatter gather part of it. It is then sending out these queries to your indexes, to your shards, to your index shards rather, getting back the results from them and then merging them. Again, an important but subtle difference between web search and e-commerce search, right? In web search, typically the sharding is done in a random fashion. There is no kind of, all documents are more or less similar to a web search engine, and it just computes some random hash and then splits them up. That's not the case for us. What we do is we try to shard them at a very high level based on some category. What I've shown here is that we have 3 shards. One is looking at the books, one is looking at lifestyle, which is basically fashion or your clothes and so on, the other is electronics. Now, why is this useful? The reason it is useful is oftentimes based on the query, we can immediately figure out, hey, this query is for electronics. I don't even need to send it to the other shards, right? And that helps us in sort of reducing the loads on our main workhorse, which is the indexer. Now, within each of these shards, you have the other dimension where I might have more than one shard, that is done randomly, and for each shard again you have a replica to scale horizontally. Fairly standard distributed architecture. And at the bottom what I've shown is the ingestion pipeline. We'll go into the details of it a little later. So that's how the functional view maps onto the architectural view, and that's really how our system looks like. Now let's talk a little bit about ingestion. So what ingestion is doing is, as I said, on the left hand side are your data sources, your other systems within Flipkart who are giving you up-to-date information about all your products and listings. You know, is there a new product that was introduced? Did this product change a particular specification? Did the product change a price? Or is there now a new offer that is associated with this product, so on and so forth. We take all of that information. There is, and different systems for, you know, all of these systems came up in an organic way. Some apply a push model, some have a pull model, and so on and so forth, which is why we have this component called the ingester. Now Sherlock and all are sort of internal code names that we use, so but don't ignore those for now. So what this ingester does is it keeps listening to these updates, and whenever an update happens, it sends the update to a Kafka queue, and it also writes it to a persistent store in the form of an HBase. Why do we need that? Now remember, each of these systems gives me a snapshot. It says that for this listing, the price is now 530 rupees. It does not tell me what the delta was. So the action I need to take depends on the delta. What did something change for this product, and if so, what was the change? As a result of which I need the last snapshot to compute the delta, and that is why I need a persistent store. Now what the Kafka queue does, there are storm topologies and there are more than one of them. There is typically one topology or more than one for each type of data source. It is listening to updates on this Kafka queue. It is, once it sees an update, it knows that something has changed. It goes to the persistent stores, figures out the delta, and based on the delta, it takes an action, right? The action typically is some form of an update that goes to your Solar or Lucene master. And from the master, the update propagates to all your slaves, right? So that's typically how a update flows through our system. Now, you know, I made a big deal about the attributes, these categorical attributes that keep changing. And let me tell you a little bit about how we dealt with those attributes. So last year in 2016, there's a Solar Lucene conference called Solar Lucene Revolution, where we sort of showcase this technology. What we have done is we have taken the base Solar Lucene index and we have added a very custom in-memory data structure to it, which is extremely efficient and allows you to index and look up these categorical attributes like pricing, availability, serviceability, and so on and so forth, right? And that's why you're seeing these updates going into that in-memory data structure where each of the shards keep listening to these categorical updates and very efficiently updates its internal data structure. When we score the documents, because they are in memory and can be looked up very fast, we can afford to do the kind of scoring in sub-second kind of timings for a lot number of documents, and also we can afford to update these attributes very quickly. Now, what is different from a typical web search index is we are not updating the entire document. Only partial aspects of the document, some of these categorical attributes are being updated. Because if we try to update the entire document, the text part of it, that is very expensive. For people who are familiar here with information retrieval, you have your posting lists and so on, right? Updating the posting list becomes expensive and hard. But changing the categorical attributes is typically faster if you do a good job of keeping them in the right kind of data structure. These are effectively numbers and enums, right? Now on the top you have another persistent store. The reason you need that is whenever a new shard comes up, like you're rebooting it for bootstrapping, it needs to effectively get this state from a persistent store so that it can build its data structures internally. So that's how sort of the ingestion things looks like. As an example, here is a standard topology corresponding to catalog. Catalog is one of the most complicated forms of update. Whenever a product changes its listing state, we get updates. And I think in the interest of time, I don't want to walk through this entire process, But there's a lot happening here. Like again, you're looking at what the last state was. Did the product go from an active state to an inactive state, or an inactive state to an active state? And as I said, depending on the delta, you need to take certain types of actions. And that's what this topology is showing you. Like if it's going from an inactive to inactive, there's nothing to be done there. Or an active to active, but then what attribute change? Only change that part in solar. So as I said, that was kind of the very high level overview of our search platform, the two big components, ingestion and serving. Let's now focus onto the relevance and ranking part of it, right? Again, there are three topics that I wanted to cover. What is challenging about e-commerce search? Why is it hard? Then I wanted to take you through typical processing that we do on top of a user query to understand it better, to improve it, and so on. And finally, I'll talk about a couple of illustrative problems, the kind of projects, the data science projects that we are doing to improve our relevance ranking. I mean, that's kind of the bread and butter of the search quality team, right? Keep improving how good your search results are. So one thing I forgot to mention earlier is that Flipkart is neither a pure play hybrid model, neither a pure play retail e-commerce, neither is it a pure play marketplace. It is hybrid. And the marketplace aspect of it imposes certain challenges. Like as I said, there are 100,000 sellers. One of our top alpha sellers or our internal own subsidiary, the kind of information they will give about the product in terms of its description, in terms of its specification, and so on and so forth, is very different from what a third party seller, literally your mom and pop store will give you. Now we get a lot of missing values, spell correction, like spelling mistakes in the catalog information itself when it comes from our sellers. On top of it, there is sort of malicious or maybe unintentional spam that is happening. You might be selling a simple cases and covers, and in some field that we have given them for different reasons, they might stuff in keywords like iPhone 6, iPhone 7, Samsung, and so on and so forth, right? So when you try to do your text matching, for iPhone 6, this some case and cover for 150 rupees is going to come up. So we don't fully control our documents, and that's what we need to deal with. On the user side, India is a very diverse country. The languages spoken across states are very different. You have users across all spectrums of economy. Like some people can afford very expensive products, some people are looking for more value for money. So when a query like shoes happens, you don't ideally want to give the same answer to all of the users, right? You want to personalize for them, figure out what their affinity for price is, what kind of price segments are they operating it in, and so on and so forth, right? And those are some of the other challenges. And in terms of the ecosystem, right, as you might know, about 70-80% of our users are on mobile apps, and they are using your 2G, 3G networks like Jio and so on, which don't have the most sort of best data rates out there, and that imposes another set of challenges. So for example, I'll give you a simple thing, right? When you start typing in a query, if you have a very fast network, you will get back the auto suggest result, auto complete results, and we will quickly sort of pivot you or guide you into the right kind of query that you want to do. And it's then easy to select a query and issue it. But if that response does not come fast enough, then what you end up doing is you end up typing the query on a mobile, and you will start making spelling mistakes. Anytime your query is misspelled and so on, there's a good chance that its relevance will go down, because then it imposes more challenges, or the onus is on us to understand that query at that point in time. So as I said, different people coming from different parts of India with different literacy, they don't know the spellings of a lot of products or brand names and so on. You have to deal with those. The buying power of people varies from region to region, and again, you need an element of personalization to kick in there to be able to have relevant and useful results. So let me give you some numbers in terms of the diversity that we see, right? First of all, here this graph shows you how much growth we are seeing in the tier 3 cities. We live in metros, but the real growth is happening from the tier 3 cities as far as Flipkart is concerned. So more and more users are coming to our platform from there. Now, what is different about tier 3 cities? Take Samsung. It's a misspelling of Samsung. Almost 2 times more likely that this misspelling will happen from a tier 3 city versus a metro, right? Take the misspelling of jeans. 3 times more likely to happen, two and a half times more likely to happen from a tier 3 city versus a metro. So we have seen transliteration of Hindi names, like people are looking for shoes and they type in juta in English, right? And we have to still make sense out of it, right? This is actually a flowchart from from Ron Kohavi, who's talking about what usually happens in web search when a query hits in. What do most IR systems do? So they go through a fairly standard process of rinse, lather, and wash. First, the moment your query hits in, you do some kind of normalization, lower casing, removing extra spaces, removing some special characters, and so on and so forth. Next comes your spelling correction. After that, you have some segmentation, like Red Tape, for example, is a popular brand in shoes. So you don't want to treat this as two different words. The meaning is very different if you treat them as two different words versus a compound word like red tape, for example. Right? The kind of documents you will match would be very different. After your segmentation, you have your stemming to do some form of normalization, another form of normalization, and then you're annotating the query. Maybe you're adding some synonyms, and finally you have the rewrite part of it that goes to your index. So fairly standard flow. Now let's see how we are doing it in the context of Flipkart. I'm sorry, I know it's a little busy slide, but the idea was to give you the different phases that are there in our query understanding. So let's talk about a few of those boxes. The first one is normalization. The moment query hits in, we do lower casing, some string cleanup, removing superfluous spaces, and so on. The second thing we do is spell correction. So in spell correction, it's done in two ways. One is at the term level, so where I look at individual terms without the context of the rest of the query, and I'll change it if it's a misspelling. And the other is a whole query rewrite, where I look at the entire query. I know that it should be rewritten in some other form based on some past data that I've seen, based on some machine learning models that I've built. So both these happen. Post that, as I said, we take help of our catalog, where we know that, okay, this is Red Tape, Louis Vuitton, etc. are segmented words or compound words, and we identify those in the user query and mark them that way, so that we don't split them in looking up in the documents. From there, you go to the stemming. We do a fairly conservative stemming, just pretty much removing plurals, that too in specific cases, and so on. We have tried a more aggressive stemming, and that has not gone well. So we are fairly conservative with that. Followed by synonymization. And I think the most critical part here is the intent part, what I'm referring to as deduction and tagging. And that's kind of the most interesting part, in the sense that given a textual query, or let's say you have done all your spelling correction and so on and so forth, how do you understand the structure in the query, right? It involves techniques like natural language processing and so on. Like, for example, the example I gave earlier, black shoes under under 1,000 rupees, or cases and covers for Samsung Galaxy E6. The reason cases and covers for Samsung Galaxy E6 is a good query to understand. Remember, Samsung is not the brand we are looking there for. We are looking there for a product that is compatible with this particular phone. So, it just highlights the challenge that just because I see Samsung and I know it is a brand doesn't mean that I'm looking for products with brand equal to Samsung, right? And those are some of the challenges that we need to address. After we have done the intent detection and so on, as I said, we do a few more steps, and at the end of the day, we come up with a query that we send down to Solar and Lucene. So, in the rest of the talk, I just want to cover a couple of techniques. These are more machine learning, data science kind of techniques, which are part of the boxes that I mentioned earlier. Like, how do you do spell correction, right? And there is no silver bullet to it. There's no one algorithm out there that's going to work for you. And you have to try different algorithms and try a union of these algorithms. And what I've mentioned here on the slide is there's a very simple pattern. Like, for example, we have seen in the case of mobiles that people sometimes type in words without the spaces in between. So we canonicalize all of these and then we say that, okay, what was the correct query for something that looks like LG Nexus 5 without the spaces? And the correct query is LG space Nexus space 5. There's no rocket science to it, but a simple pattern like this in the context of the fact that we have 80% of users on mobiles typing in very fast helps us correct the queries in this way. So these techniques are going from very specific ones to more generic ones. The specific ones address a very small slice of your query segment, but they're typically accurate and their precision is very high. As you go down, your coverage increases in terms of the number of queries you will affect, but your precision goes down. So there's a standard precision recall trade-off that you will see in these different techniques. The second most important technique, and a very simple one, is again counting. Now, if you've seen 100,000 times a pattern like you do Samsung and it doesn't give you good results, followed by which you do Samsung and you get good results, then we learn that from our query logs that this is a rewrite of the other sort of. The counting can be done in a context aware way. Like you might do counting saying that what was the word before Samsung, and in that context only apply the rewrite, not otherwise. From there we have applied language modeling techniques wherein for every query we kind of figure out what is the probability that we will see this query based on the occurrence of the words in it, the individual probability of seeing those words and so on. And a fairly standard spell correction technique is when a query comes in, if it has a low probability based on your language model, figure out if there is another query with a very small edit distance that has a very high probability, right? And finally, these days we've started using deep learning and other things where we embed these queries or their words into a high dimensional space and we look at sort of what are the near neighbors and so on. So those are some of the problems and techniques that we have seen in the context of spell correction. Query intent detection, actually, this is a very big topic. I don't think I can cover it here. I just wanted to tell you the problem statement and mention the different techniques we have used. So what is intent detection, right? So look at the first query, red tape shoes. If I were to write it as a structured query, it is telling me that I'm looking for products from the store. Store is just basically a node in our ontology tree or our catalog tree, right? I'm looking for products from this node in my ontology with brand equal to red tape. Or let's look at the second query, kids party dress 4 to 5 years pack of 2, right? Again, you can see that what you're looking for is a product ideal for kids, occasion. So all the things that I've put in boldface in braces are the features that are there in our catalog, and these features vary from store to store, category to category. Like the feature occasion does not make sense for mobiles, but it makes sense for dresses. So what I'm looking for is ideal for kids, occasion is party, store is dress, size is 4 to 5 years, and pack off is another attribute, right? Fairly complex query to understand, because the moment I understand the query in this form, I become very good at answering the query, because then it kind of becomes a fairly structured database query, and I don't get a lot of bad hits because of text matching. Samsung E6 cases, I think I gave this example earlier. I'm not looking for brand equal to Samsung here, but I'm looking for something that is compatible with Samsung E6 in the store cases. Now, the three techniques that we have tried is memorization, where for a query, what we have seen in the past, after doing this query, what do people click on? And from that product, I understand that, okay, what people are clicking on are products with brand equal to Samsung, right? So you build kind of a fairly simple probability model on top of it. Right, 80% of the people go to store equal to mobiles, 20% of the people go to store equal to cases, and you build a model in that form. But the problem with it is it does not generalize. When I see a new query for which I don't have data, I can't do much about it. From there, we have built a language model, and the most recent one that we have tried out is CRFs, conditional random fields. Conditional random fields are Bayesian models which sort of which assume that every query has a pattern to it, like in the sense the next word depends on the previous word and so on, and then you build a model on top of it, and this has given pretty good results to us. Final part I wanted to cover was in the ranking piece, and this is a very simple work that we did in the context of price personalization. Here, personalization is not hyper personalization in the sense that I'm giving Amit very different results from Prashant, but every user is basically put into some buckets or segments, and every segment sees a different types of results. So what we have done effectively is we have taken a user's past activity on our platform and bucketed every user into 5 segments. Furthermore, we don't do this at a global level, but we might do it at every store level or a category level. So I might learn the fact that Mayur buys more expensive stuff when it comes to watches, but he buys more cheaper or value for money stuff when it comes to clothes, right? My taste in one might be, my price affinity in one store might be different from the other, kind of thing. And then there's always a fallback global model. And the challenge here is that most users will not have a whole lot of activity on our platform. They haven't bought a whole lot of stuff from us. So then how do you still get their price affinity? The one thing that we noticed is just your browsing behavior. What queries you do, and post the queries, what products you look at, very quickly tells us what your price affinity is. So as a rule of thumb, what we noticed is that just by looking at 4 or 5 products, page views, right, product that your product clicks, we can very quickly tell you what your price affinity is without seeing any purchase from you. And those kinds of patterns help us very quickly segment the users and personalize the results for them. For every store, then what we do is we take the products as well, we further segment them into these 5 buckets or something, and when a user comes in, we again figure out which bucket you belong to, and then we try to promote products that are from the same price bucket from that category. So there's kind of a boosting function if it matches your segment, and kind of, you can imagine, or a neighboring segment but falls off rapidly for other segments. So a simple trick, nothing very fancy. You could imagine that you could, a natural progression to something like this is building kind of a machine learning model which takes in many features, not just your price affinity, but your brand affinity and your geography, maybe your phone, whether you're using an iPhone versus are you using an Android, and so on and so forth, and building a more complex engagement model in the sense that how likely are you to click on this product, how likely are you to purchase this product and use that. So that is kind of the natural progression that we have started on when it comes to personalization. So that's it. I mean, the idea was to give you a flavor of the kinds of problems that are there, the challenges, and sort of talk both on the systems aspect, the architecture, and also give a little bit about the query understanding and the ranking relevance piece. And hopefully, you've come out of the talk figuring out how, or at least appreciating the fact that this is different from web search, why it is different from web search, and the underlying challenges. Thank you very much.